In this video, I'll be discussing about isomerism in coordination compounds. Before we move on to the types of isomerism, let me give you the definition of isomer and isomerism. Two or more compounds having the same molecular formula but they have different arrangement is called isomer, and the phenomenon is called the isomerism. Now moving on to the types of isomerism in coordination compounds, we have basically two types, that is structural isomer and the other one is stereoisomer. Structural isomers are those isomers which have same molecular formula but they differ in structural arrangement, whereas stereoisomers are those isomers which have the same position of the atoms or group of atoms but they differ in the spatial arrangement around the central metal atom. Under structural isomer, we have the following types of isomerism or isomers, that is ionization, hydrate, coordination and linkage. Under stereoisomers, we have geometrical and optical isomerism. So let us go one by one. The first one is ionization isomerism, which is under structural isomers. Ionization isomerism or ionization isomers are those isomers which have same molecular formula but they give different ions in solution. Say for example, these two, okay, they have the same molecular formula, okay, Br, SO4, SO4 and H35, NH35, but in solution, okay, the ions that they will give is, here it will be SO4 2 minus, here it will be Br minus. Okay, let us see another example. In this case, the ions that will give is, this will be Br minus and this will be Cl minus. Okay, so this is about the ionization isomerism. Okay, so that means like the isomers which have the same molecular formula but they give different ions. Okay, they give different ions in solution is called ionization isomer, and the phenomenon is called ionization isomerism. The next one is hydrate isomerism. We also call it as solvate isomerism. Okay, now the hydrate isomers are those isomers which have the same molecular formula but they differ whether the solvent, okay, here the solvent is, okay, we consider solvent as water, okay, solvent as water, whether the solvent is directly attached to the central metal atom or not. Let us see one example. In this case, the water is directly attached to the central metal atom, okay, for the first example, and in the second case, the solvent water, that is the water, is not directly, okay, is not directly attached to the central metal atom. So this is one example of hydrate isomerism. Okay. The next one is the coordination isomerism. The type of isomerism occurs in those compounds which contain both the cationic as well as anionic entities, okay, and the isomers they differ in the distribution of the ligands. Say for example, here you see one is cationic complex and the, or like cationic entity and the anionic entity, okay, and there is a difference in the distribution of the ligands. In this first example, you see NH3 is with CO, whereas CN is with Cr. But in the next example, you see CN is with CO and NH3 is with Cr, provided the molecular formula remains the same. So this type of isomers are called coordination isomer. Okay. Stereoisomerism, the first one we have is geometrical isomerism or geometrical isomer. Here the ligands they occupy different positions. Okay, so the first one can be like the ligands or the like ligands can be adjacent to each other, which we call it as cis form, if the ligands are opposite to each other, we call it as transform. The geometrical isomerism are possessed by these two type of structure. One is called the square plan, one is called the square planar, and the other one is octahedral. We also have tetrahedral for the coordination number 4, but for tetrahedral, since all the ligands are adjacent to each other, therefore it did not possess any geometrical isomerism. Okay. Now let's see the first one for the coordination number 4. Okay, that is square planar. If it is of this type, MA2 B2, then the cis form will be MAA BB. Okay, the same ligands will be adjacent to each other. Okay, we shall consider only one of the ligand, either one. Okay, then for the transform, the same ligand will be opposite to each other. Say if we consider A, then it will be on the opposite side. Okay, the other A. So this is the transform. Now for coordination number 6, which possesses octahedral structure, if the complex or the components of the form, okay, then the cis form will be this M adjacent to each other, and therefore this is cis form. And for the transform, we will represent it as this is B B, okay, A. So this is the transform. Now there is another form for the octahedral structure. Okay, it can also be of this type, that is MA3 B3. Here we shall not name it as cis or trans. Okay, here we have two types, that is facial and meridional. Okay. In short we name it as SC, and this one in short we name it as MER. Okay. Now for facial, okay, the three same ligands will be on the triangular face of, or on one of the triangular face of the octahedral. Okay, so that is, see, A. Okay, they are on the same triangular face. Okay, same triangular face of an octahedral. Okay, these three same ligand will be on one face of the octahedral, whereas meridional, those same three ligands, okay, if we consider A, okay, those same three ligands will be on the equatorial. Okay, that is like this. Okay, so these three same ligand will be on the equatorial. So this is geometrical isomerism. Next one is optical isomerism or optical isomer. Okay, here there are certain substances that can rotate the plane polarized light. Okay, that can rotate the plane polarized light, and those compounds are called optically active substances. So say for example one compound, after forming the mirror image, say for example here in this case the mirror image of this one is this. Now they are both non-superimposable. Okay, now such substances are called optically active substances. Okay, the first one is the dextrorotatory, the second one is the labiorotatory. Okay, now how do we find the dextro and labiorotatory? Is if the isomer rotate the plane polarized light to the right, it is called dextro, okay, dextro-rotatory, and if it rotates the plane polarized light to the left, it is called lavio-rotatory. Okay, so that's all about the isomerism. Okay, and one more thing, you can try out this one, okay, for this particular optical isomerism and draw a similar structure like this, find out the dextro and lavio.